Hello everyone. So in this lecture we will review some general aspects of chemical kinetics. Now this topic or the discussions that I am going to cover can be found in any standard textbook on physical chemistry or in any textbook on chemical kinetics. The textbooks which are referred to you, these textbooks cover the entire portion which I am going to discuss. So the first thing we study in chemical kinetics is about the rates of the reactions. And then the first thing we study is suppose we have a balanced chemical reaction which I am writing in a most general way, that I have some reactants which are A and B, capital A and capital B, and they react together along with some other reactants, and then they produce some products which are C and D, capital C and capital D, and maybe some other products. And the stoichiometries are given as small lowercase symbols like A, B, C and D. Now for this reaction we can define the rate of the reaction, which can be expressed either in terms of the reactants or in terms of the products. Now the rate is always expressed from the stoichiometric equation, and as you know that the rate often we call it as denote it as V, because V is basically the velocity of the reaction, and we write it, if I write it in terms of the reactant A, I'll write it as dA dt, where the A inside the third bracket denotes the concentration of A, and then we have to divide by the stoichiometric number with a negative sign, because the negative sign is indicating that this is a reactant, it is being consumed over time. So the concentration of A is decreasing over time. The reason is we have actually chosen this reaction to be irreversible, because I have written it as a single arrow, and we could also express it in terms of the other reactant B. So for that it will be minus 1 over small b d concentration of B dt. Similarly, we could also write it in terms of the product concentrations. Now remember that the products are actually growing in time, so instead of a minus sign we will have a plus sign here, and I will have 1 over C d concentration of C dt, which is equivalent to also writing 1 over D concentration of D and dt. So all these terms are actually equivalent to the unit advancement of the reaction. Now advancement is or the progress of a reaction we define when we discuss the thermodynamics of reaction, how the Gibbs free energy changes. And you can go back and look at your textbooks which are recommended to you, what is the meaning of advancement. And in this case the overall rate of the reaction can be shown that this is the advancement per unit time per unit volume, that is defined as the rate of the reaction. Now this is the overall how I can express the rate, but then experimentally the rate is found to vary with concentrations of the reactants. It can also vary with the concentration of the products in rare cases. Now if we find this rate, which can be expressed as either of these terms, like 1 over A dA dt or 1 over B dB dt with the negative signs, or in terms of the products, so that rate, suppose we find it to be equal to some constant times the concentration of A raised to the powers, let's take some number m, concentration of B raised to the power some number n, something like that. Then we tell that this equation, which is basically the rate, is equal to some expression in terms of the concentration. That equation we call it as a rate law. So rate law is an experimentally determined quantity. So rate laws we cannot actually predict from the concentration. I'll come back from the stoichiometric equation. I'll come back to this point once again. So this is an experimentally determined quantity, or we can just say it is basically experimentally determined equation. Now, what are these numbers m and n? So this m and n are actually orders with respect to A and B. So the order of the reaction means the number to which the concentration is raised to the power. So for this reaction, the way I have written it, the order is mth order. With respect to A, it is nth order with respect to B. Now again, this mth order or nth order, as I said, it is coming from the rate law, which is experimentally determined quantity. So order of a reaction is an experimentally determined quantity. Now order of a reaction has a meaning if and only if I can write this equation like this. Like for example, the way I have written it, that A to the power m, B to the power n. There will be cases where actually we cannot write the order of a reaction in such a nice and compact form. Then in those cases, the order of a reaction doesn't have any meaning. Now I will give you some examples of few specific reactions after which you will have an a clear idea how basically the order of a reaction has no connection with the stoichiometric rate or stoichiometric equation on the balanced chemical reaction. For example, for this reaction, say H2 plus I2 is giving 2HI, the order of a reaction or the rate law is found to be as some constant into which we call, this constant we call as rate constant, into concentration of hydrogen into concentration of iodine. Now in this case, as you see, the rate law actually resembles the stoichiometric equation, but this is just accidental. In many cases you will see that it no way means that in the reaction, the way it was proceeding, in that case hydrogen and iodine molecules came together and then they collided. The overall collision of the rate, because rate is nothing but number of collisions per unit time, it is connected to that quantity. If I have actually the reaction rate governed by a process where just the hydrogen molecules and the iodine molecules collided, then those number of collisions will be proportional to their product of the concentration terms. But we cannot just simply say that since the order the rate equation has a simple form like this, we cannot say that this reaction occurs via step where hydrogen and hydrogen just colliding and giving you the product. The reaction can have actually multiple steps. So most of the reactions actually have many multiple steps in which some reactants first collide to give you something which is known as an intermediate. Then the intermediate again forms collides with something else and forms another intermediate, and then eventually it forms product. So any composite reaction, we can say, is composed of many reactions, many fundamental reactions which cannot be divided further, and those fundamental reactions we call it as elementary reactions. So elementary reactions, we'll discuss more about it, but for the time being, just remember that the elementary reactions are those reactions which basically represent the most fundamental step of a reaction. Now as I said, most of the reactions I'm writing here are actually composite reaction. From the rate law, it may look that it is an elementary reaction, but there most of them are not. For example, I'll give another example of this type, hydrogen and the bromine reaction. Now you see that this reaction is also very similar to the previous reaction. It's hydrogen and iodine. This is instead of iodine, it is hydrogen and bromine. Now for this reaction, the rate law, which is experimentally determined quantity, is found to be a rate constant K prime into hydrogen concentration into bromine concentration divided by another rate constant, it will be 1 plus another rate constant into HBr concentration divided by Br2 concentration. Now this reaction is very interesting. Now if you look at it carefully, for this reaction I cannot write the rate in terms of simple equation, something like H2 to the power m, Br2 to the power n, something like that. So for this reaction, since I cannot write it in this form, this reaction does not have any specific order. And also you see this reaction has multiple rate constant. It's not only just one rate constant. So this expression that the rate of the reaction is proportional to, not proportional, it is dependent on H2 and Br2 concentration, but in a very complicated way, was found experimentally. And once we find it, then we propose a mechanism for this reaction where we say that this reaction does not proceed like a collision between hydrogen and bromine molecules, but rather it goes through multiple steps where the overall stoichiometry may look like that hydrogen and bromine are reacting together, but there are many elementary steps involved, and then once we work on the kinetics of these elementary steps, we should at the end of the day be able to reproduce or predict the observed rate law. Now I will give you a few more examples. Just like we gave you the example of hydrogen and iodine to give you hydrogen iodide, there is also another example, nitric oxide and oxygen giving you nitrogen dioxide. For this reaction, the rate of the reaction is found to be some rate constant times nitric oxide squared and oxygen. Now again, you may have a notion that it is probably an elementary reaction because as I see that the stoichiometries are exactly appearing in the rate law also, because two molecules of nitric oxide reacts with one molecule of oxygen, giving you two molecules of nitrogen dioxide. And in the rate equation, I find that the order is second order with respect to nitric oxide and first order with respect to oxygen. Now again, this is a wrong concept. That the reason is what we are saying is two molecules of nitric oxide collides with one molecule of oxygen, and that kind of collision probability is very less, because collision probability for gas phase reaction are mostly bimolecular. Probability of three body collision is very rare, because you can remember that you can argue always that the probability of three bodies simultaneously colliding to each other will be much lower than the probability of two bodies colliding together. So we exclude that possibility, and we say that although the overall order for this reaction is 3, by overall order we mean the sum of the orders for individual reactants, and although the overall order is 3, this reaction is not a trimolecular elementary reaction. It is composed of many reactions. Now a similar looking reaction, which is nitric oxide reacts with hydrogen here, and to produce nitrogen and 2H2O. Now for this reaction we find that the rate is equal to nitric oxide squared and then concentration of hydrogen. Now here you see that although there in the stoichiometry there is a number 2 in front of hydrogen, it doesn't appear in the rate law. So you cannot predict anything about the rate of the reaction, how the rate law will look like, and what is the order of the reaction which is obtained from the rate law. You cannot predict from the stoichiometric equation, which is the balanced chemical reaction. Now we'll give you two more examples where you will see that how it is very different. This rate law can be for a very simple reaction. Now the fifth example I have is the decomposition of acetaldehyde into methane and carbon monoxide, and again for this reaction the rate law is found to be some rate constant into acetaldehyde concentration raised to the power 3 by 2. Now you can see that the rate law is now the order of the reaction is fractional. So order of the reaction in this case is a unique example where it is fractional. One more point I wanted to make here is that when we talked about the hydrogen and bromine reaction in the previous example, so you see that here the HBr also appears in the equation of the rate equation, which means the product can also influence the rate. Now in this case, as you see, the HBr appears in the denominator, meaning as the HBr is forming, the rate of the reaction will be decreased, which means actually this is an example of inhibition, in sense that formation of the product can actually suppress the reaction. I'll give you one more example, which will be the last example of this kind, and this is also seemingly very simple reaction, that chlorine and carbon dioxide reacts to give you an adduct Cl to CO, and the rate of the reaction was found to be chlorine raised to 3 by 2 into carbon monoxide. Now you can see the complexity of the rate law, and it is fractional order with respect to chlorine, it is first order with respect to carbon dioxide. So the bottom line again here to discuss all these things is that you cannot predict a priori anything about the order of the reaction or the rate law just by looking at the stoichiometric number. Now we will move on and we will talk about the integration of the rate law. Now suppose I have a reaction, again something like a general reaction, and I find experimentally that the rate of the reaction and for the timing, let us say the 1 by A, or we can actually keep the 1 by A. Suppose it is found to be varying with nth power of A. Now I can actually, instead of writing it as 1 over A, this A can be absorbed into this rate constant, and I can actually rewrite it like this, minus dA dt, which is the rate law, and or the expression for the rate, and the rate law is found to be some rate constant into A to the power n. Now this is known as the differential rate law. So from a differential rate law, what we do is that we integrate it, and when you do the integration, all of you know that we need some limits of integration just to get rid of the constant of the integration. Now in these cases, we always say that at initial the concentration, when at time was at 0, when the reaction was started, the amount of A was, say, A0. We'll denote it as A0. So A suffix 0 denotes the concentration of A at time 0. Now if we can actually integrate it, and the integrations are you have already studied, I hope, the integration of the rate law. So for if n is equal to 1, which is known as a first order reaction, because it is raised to the power n, so the order of the reaction, as I have written here inside the box, is nth order. Now if n is equal to 1, so I can get I can integrate this equation very readily, and I'll get a first order rate expression. Now also for how, if we want to plot the first order rate expression, it will be just an exponential decay with respect to time. So from an initial concentration of A0, at any time A actually decreases exponentially with respect to time. Now we can also define a quantity which is known as the half-life of the reaction, which is defined as the time taken for the reactant to fall to its half value of its initial concentration. Now we can easily figure out, we have to just put A to be A0 by 2, and then we can solve it, at what time that happens, and you will get it as natural log of 2 divided by the rate constant. Now only for first order reaction, the half-life is independent of the concentration. Now if you ask this question, what happens for n not equal to 2, then the rate law looks like this. So we'll have say A raised to the power minus n plus 1. It's a very simple integration, and you can actually look up the textbooks that are recommended, or you can also look up the YouTube videos for the course on thermodynamics and kinetics, or introduction to thermodynamics and kinetics. And we'll have A raised to minus n plus 1 and divided by minus n plus 1 is equal to kT. Now, as you can see that for this reaction, this is a general reaction for n not equal to 2. For this reaction, if we calculate the half-life, so this half-life expression, you can again calculate it. Instead of A, you just put it as A0 by 2, and naturally there will be a factor which is 2 to the power n minus 1 minus 1, and we'll have n minus 1 into k into A0 raised to power n minus 1. Now the point here is, for any reaction which is not a first order reaction, the half-life actually depends on the initial concentration A0. For a first order reaction, only for a first order reaction, the half-life is independent of the initial concentration. No matter which concentration you start with, the half-life will be independent. The examples are radioactive decay, which actually depends only on the concentration of the radioactive material present at any time, and so it follows a first order rate law. And we see that there actually half-life is a very important quantity to tell about a particular species, and we always say, for example, this isotope of plutonium has this half-life, and that is the meaning of that. But for any other reaction which is not a first order, where actually n not equal to 2, their half-life is directly connected to the initial concentration, so it will matter what you started with. Now, as you see here, most of the cases usually the textbook discuss about the second order reaction, where n is n is basically this should be actually n not equal to 1. Say for example, if I take n equal to 2, so n can be 2, 3, 4 or anything. It can be also a fraction. Now suppose if I take n equal to 2, then I can actually reduce this expression. As you can see, it will be minus 2 plus 1, so it will be 1 over a, something like that, and so I can reduce it. I can go to the next page and I can just write it down there. So for any second order reaction, as you can see here, we can start from here. So if n equal to 2, we'll get, just follow this equation. What we are getting, we'll get 1 over a minus 1 over a0 is here I'll get minus 2 plus 1, which will give me a minus sign, so that will be minus kT. So this expression you have seen for a reaction which is second order. Now similarly, we can also derive the rate law for any nth order, for example third order reaction. Now often for a second order reaction may involve not just a square, but it can be actually first order with respect to two species. In the sense, what I am saying is that the rate law, which I can write in terms of the concentration of or the decomposition of product A or the decomposition of product B. I'm not writing the stoichiometries. Let us just write it the stoichiometries, but eventually we can actually absorb the stoichiometries again in the rate constant. And then if it is found that the rate law is something like this, now actually it is different. It's not like a square. It is dependent on A and B, so it is first order with respect to A and first order with respect to B, but the overall order is still 2. So which means it is still a second order reaction, but it is a slightly different second order reaction. So we can also integrate this second order reaction, and what you will get the integrated rate law after you set the initial condition that at t equal to 0 the concentrations were A0 and B0, and also some stoichiometric balance that at any point, if I take the concentration of A and B together, that should be equivalent to their sum of initial concentration. If I apply those conditions, then I can actually integrate this equation using those initial condition as well as this mass balance, and what we get is something like this, the integrated rate law, which will be ln B by B0 divided by ln A by A0 is nothing but equal to B0 minus A0 into KT. Now you see that moment we change the condition that I have in the rate law, two spaces involved simultaneously, I'll have a slightly more complicated expression for the integrated rate law. So all these equations have been derived in the earlier course on Introduction to Chemical Kinetics and Thermodynamics. So I'm giving you an overview just to make sure that we can actually proceed with the basic concepts of chemical kinetics. Now so far what we have discussed, let me summarize that we discussed what is the order of the reaction, and we emphasized this point again and again that the order of a reaction which is an experimentally determined quantity has nothing to do with the stoichiometry of the reaction. You cannot a priori predict the order of a reaction just by looking at the stoichiometry of the reactions. And we gave you few examples of real life examples how for few reactions what are the experimentally determined order, and we found that there is no correlation. Sometimes you may accidentally get a correlation, but that doesn't mean that the reaction is proceeding via that particular pathway, which we will be discussing later. And then we gave you few specific examples, like if the order is found to vary as a to the power n, and we gave you not the order, the rate of the reaction is basically found something like that, or something like A into B, and we showed that for those cases we can actually integrate the differential equation, which is the rate law, in an integrated form, so that we can find actually the amount of A at any time or amount of B at any time. So now we will be discussing about a few specific examples which will be necessary for the subsequent discussion to understand the mechanism of chemical reaction.